At the heart of some galaxies lies an engine that has nothing to do with stars. An active galactic nucleus is a galactic core whose prodigious output comes not from nuclear fusion, but from gravity, from the energy released as gas spirals inward and falls onto a central black hole of millions to billions of times the mass of the Sun. The most luminous of these, the quasars, can outshine an entire galaxy of hundreds of billions of stars, and they do it from a region scarcely larger than our solar system. This chapter builds the physics of that engine, how accretion liberates energy with an efficiency that dwarfs fusion, how a single black hole regulates its own appetite, and how the bewildering zoo of active galaxies, Seyferts, quasars, radiogalaxies, blazars, resolves into essentially one kind of object, seen from different angles. And it ends with the deepest surprise of all, that these tiny engines have shaped the very galaxies that host them. The story begins in the early 1960s, when two threads of astronomy converged. Since 1943, a handful of spiral galaxies had been known to have unusually bright, broad-lined nuclei, the Seyfert galaxies, but their importance went unrecognized for 20 years. Meanwhile, radio surveys were turning up hundreds of discrete sources, and a few of them coincided not with obvious galaxies, but with what looked like ordinary stars, whose spectra showed broad emission lines at wavelengths matching no known element. The puzzle broke in 1963 with a source catalogued as 3C273. Using the Moon to occult it and fix its exact position, astronomers pinned it down, and with that position in hand, Maarten Schmidt obtained its spectrum and made the leap. The strange lines were ordinary hydrogen, shifted far to the red by the expansion of the universe, placing the object some 2 billion light-years away. The implication was staggering. If 3C273 lay at so vast a distance, then to appear as bright as it did it had to be radiating something like 100 times the output of the entire Milky Way. Yet it flickered, varying in brightness over weeks and months, and that put an iron limit on its size. Nothing can brighten coherently faster than light can cross it, so a source that varies in a month can be no more than a light month or so across, a region no bigger than the solar system, outshining a galaxy. No conceivable assembly of stars could do this. These objects were named quasi-stellar radio sources, quasars for short, and the crisis they posed was resolved by the end of the decade, when Salpeter, Zeldovich, and Lindenbell argued that the only engine equal to the task was gravitational accretion onto a supermassive black hole. That reasoning is the foundation of everything that follows. Why is gravity such a potent power source? As gas falls toward a black hole, it cannot simply plunge straight in. Carrying angular momentum, it settles into a swirling accretion disk, and friction within the disk slowly transports that angular momentum outward, letting matter spiral inward and converting its gravitational energy into heat and light. The efficiency of this is extraordinary. The hydrogen fusion that powers stars converts about 0.7% of rest mass energy into radiation. Accretion onto a black hole liberates the binding energy of matter at the innermost stable orbit, and that is far greater, from about 6% for a non-spinning hole to as much as 42% for a maximally spinning one. Accreting black holes are, quite simply, the most efficient steady power sources in the universe, which is why swallowing only a few suns' worth of gas per year suffices to light a quasar. But accretion cannot proceed without limit, and the ceiling has a name, the Eddington luminosity. As the engine brightens, the outward push of its own radiation on the infalling, ionized gas grows, until at a certain luminosity that push balances the inward pull of gravity. Beyond it, radiation would tend to blow the fuel away and choke off the supply. This Eddington limit rises in direct proportion to the black hole's mass, so a 100 million solar mass hole can shine comfortably brighter than a whole galaxy of stars before reaching it. The ratio of a source's actual luminosity to its Eddington limit is a key measure of how hard it is feeding. Luminous quasars radiate near that ceiling, while the starved black hole at our own galaxy's center sits many millions of times below it, in a dim and inefficient trickle. The same limit sets a maximum rate at which a black hole can grow, a ceiling that will haunt us when we ask how the earliest giant quasars were built. The standard picture of the accretion disk was set out by Shakura-Sunyaev in 1973. Unable to derive the turbulent friction from first principles, they bundled all their ignorance into a single adjustable parameter and, remarkably, still extracted a robust prediction that the disk's temperature climbs steeply toward the center, so the inner regions are the hottest. For a supermassive black hole, this places the peak of the thermal emission in the ultraviolet, producing the characteristic big blue bump seen in quasar spectra. For decades, the physical origin of that friction was a mystery. It is now understood to be a magnetic instability that stirs the disk into turbulence wherever a magnetized gas orbits a central mass, vindicating the spirit, if not every detail, of the original prescription. Around this engine sits a set of nested components, and knowing them is the key to the whole subject. Innermost is the disk itself, radiating the ultraviolet glow. Just above its inner reaches lies a tenuous, blisteringly hot corona of electrons, which scatters the disk's photons up to X-ray energies, giving every active nucleus its hallmark X-ray glare. Some of those hard X-rays strike the disk and are reflected, stamping the spectrum with a fluorescent line of iron, and when that line is emitted from the very innermost orbits, it is smeared and skewed by the immense gravity and rapid motion there, becoming one of our few probes of how fast the black hole spins. Farther out lie the line-emitting regions that give active nuclei their spectra. Within a few light days to light months sit dense clouds of gas, whipping around at thousands of kilometers a second, and lit by the central engine, emitting the broad emission lines that define one class of active nucleus. Farther still, across tens to thousands of light-years, thinner gas moves more sedately and emits narrow lines, and surrounding the whole inner engine is a thick, donut-shaped ring of molecular gas and dust, the torus, whose inner edge is set by the radius at which the central glare is fierce enough to vaporize dust grains, and which absorbs the engine's radiation along its own plane and re-emits it in the infrared. Modern observations suggest this torus is not a smooth donut but a clumpy, perhaps wind-blown structure. That geometry yields a beautiful way to weigh the black hole, called reverberation mapping. The central engine flickers and the broad-line clouds, lit by it, flicker too, but a little later, after the light has crossed the intervening distance. Measure that delay, multiply by the speed of light, and you have the size of the broad-line region. Combine that size with the speed at which the clouds orbit, and the black hole's mass follows from the simple physics of gravity. Better still, campaigns across many objects revealed that the size of the broad-line region scales with the square root of the engine's luminosity, exactly what you expect if the clouds everywhere feel the same intensity of light. That single relation lets astronomers weigh a black hole from one spectrum, and so estimate the masses of hundreds of thousands of quasars across the sky. By the 1980s, the catalogue of active nuclei had splintered into a confusing menagerie of types, and the central question was whether these were truly different beasts or one beast seen differently. The answer, crystallized in the unified model, was largely the latter, and the decisive evidence was a trick of the light. The nearby galaxy NGC 1068, whose direct spectrum shows only narrow lines, was examined in polarized scattered light, and there in the light bounced toward us off gas above the nucleus, the hidden broad lines appeared. The interpretation was compelling. The galaxy does harbor a normal engine and broad line region, but our direct view is walled off by the dusty torus. We glimpse the buried nucleus only in reflection. The torus, in other words, is real, and orientation determines what we see. From this follows the basic division of the radio-quiet majority. When we look down through the opening of the torus, straight at the disk and the broad-line clouds, we see a Type 1 nucleus, broad lines, a strong blue continuum, unobscured X-rays. When instead our sightline grazes the torus edge-on, the inner engine and its broad lines are hidden, and we see only the narrow lines from the gas farther out, over an engine whose X-rays are heavily absorbed, a Type 2 nucleus. In the most extreme cases, the obscuring gas is so thick that it blots out all but the hardest X-rays. The model makes predictions that have, broadly held, hidden broad lines should appear in scattered light, the infrared glow of the torus should betray the engine's true power regardless of angle, and X-ray absorption should track the optical type. All three are borne out. A minority of active nuclei, perhaps 1 in 7 or 8, do something more dramatic still. They launch jets. These are collimated beams of plasma, moving at nearly the speed of light that can drill outward for hundreds of thousands of light-years, far beyond the host galaxy, and inflate vast lobes of radio-emitting gas. Why only some black holes make powerful jets, while most do not, remains one of the field's genuinely unsolved problems. When the jets point well away from us, we see the extended radio structure directly, and these radio galaxies fall into 2 classes named by Fanaroff and Riley. The lower power sources, brightest in the middle and fading outward, with turbulent, decelerating jets, and the higher power sources, whose jets stay sharp and terminate in brilliant hot spots at the outer edges of well-defined lobes. The transition between the two occurs at a fairly sharp luminosity, though its physical cause is still argued over. When one of these jetted galaxies is instead turned so that a jet points toward us, its whole appearance changes, and the unified picture extends to embrace the difference. Seen from the side, a low-power source is an ordinary radio galaxy, but, viewed nearly down its jet, that same low-power engine becomes what is called a Bl-Lassity object, its starlight swamped by the beamed jet, and its emission lines all but washed away. A high-power source seen side-on is a radio quasar with its full complement of broad lines. Viewed down the jet, it becomes a flat-spectrum radio quasar. These beamed objects, the Bl-Lassity objects and the flat-spectrum quasars together, are the blazars, so orientation does double duty for the jetted nuclei. The torus decides whether we glimpse the broad line region at all, while the angle of the jet decides how fiercely its beam is boosted toward us. A single engine can masquerade as a whole family of objects, depending only on where we happen to stand. The picture becomes spectacular when a jet happens to point almost straight at us. Then we are looking down the barrel of a relativistic beam, and we call the object a blazar. Special relativity transforms the emission of matter moving toward us at near light speed, concentrating and amplifying it forward in a phenomenon called relativistic beaming. A jet aimed our way can be boosted in apparent brightness by factors of thousands or more, while its receding twin is dimmed to invisibility. Beaming explains everything that makes blazars extreme: a smooth, powerful glow of non-thermal radiation stretching from radio waves to gamma rays, violent flickering on timescales of hours, and strong polarization. It is the same engine as any other quasar, merely observed from the one angle that turns its jet into a searchlight aimed at Earth. Beaming also produces one of the most startling illusions in astronomy: apparent motion faster than light. Tracking bright knots in blazar jets with continent-spanning radio arrays, astronomers see them stream across the sky at what looks like several times light speed. It is no violation of relativity, but a trick of geometry. A blob moving almost directly toward us at nearly light speed very nearly keeps pace with its own light, so the signals of its successive positions arrive bunched together, compressing the apparent motion. That such superluminal motion is seen at all was early direct proof that jet plasma really does move at relativistic speeds. The full radiation of a blazar shows two broad humps, a lower one from electrons spiraling in the jet's magnetic field, and a higher one, reaching to gamma-ray and sometimes extreme energies, from those same electrons scattering light to enormous energies. And a few blazars have now been tied to high-energy cosmic neutrinos, marking their jets as nature's particle accelerators. How is such a jet launched? The leading idea is that it is done magnetically, and the most dramatic version taps the black hole itself. Blandford-Znajek showed in 1977 that a spinning black hole, threaded by magnetic field lines anchored in the surrounding disk, will drag those lines around with the whirling of space itself, winding them into a tight magnetic spring that flings energy outward along the poles as a torrent of electromagnetic power. Crucially, this draws on the rotational energy of the whole, which can be nearly a third of its entire mass energy, rather than on the matter being swallowed, so it can keep a jet blazing even when almost nothing is accreting. It is a flywheel. The disk supplies the magnetic field, but the black hole's spin supplies the power, and the most potent jets seem to demand both a rapidly spinning hole and a disk so choked with magnetic flux that the field itself pushes back against the inflow. This mechanism gained striking support from the Event Horizon Telescope's portrait of the black hole at the center of the galaxy M87, a giant of some 6.5 billion solar masses from which a jet streams across thousands of light years. In 2019, the telescope resolved the dark shadow and bright ring at the jet's very base, and in 2021, imaging that ring in polarized light, it revealed an ordered, spiraling magnetic field wound around the black hole, just the configuration the theory requires to power a jet. That polarization pattern is regarded as among the first real evidence that the black hole's spin is being tapped in nature. What remains is to measure that spin directly, and to understand exactly how the outflowing electromagnetic energy becomes the glowing, particle-filled jet we see on the largest scales. With engine, obscuring torus and beamed jet in hand, the whole historical zoo falls into order along just two axes. One axis is whether the object launches a powerful jet, radio loud or radio quiet. The other is orientation, whether the torus hides the broad-line region, and how nearly the jet points at us. A Seyfert 1 and a Seyfert 2 are the same thing seen through the torus opening or across its edge. A narrow-line radio galaxy, a broad-line radio galaxy, and a blazar can be a single jetted engine viewed at steadily closer alignment with its beam. The distinction between a mere Seyfert and a mighty quasar is not a real break, but a sliding scale of accretion rate and black hole mass. Two honest cautions remain, though. The radio-loud divide is not explained by orientation and must reflect some real physical difference, and the neat boundaries are blurred by clumpy tori and by a few nuclei that genuinely lack broad lines. For most of the 20th century, supermassive black holes were thought to be exotic curiosities, far too small to sway galaxies, 1 billion times more massive. That view was overturned around the year 2000 by the discovery of a remarkably tight relationship, the M-sigma relation, between the mass of a galaxy's central black hole and the speed at which the stars in its central bulge mill about. The correlation is astonishingly precise, far tighter than any link to the galaxy's total mass, and that tightness is the crucial clue. The stellar speed measures the depth of the gravitational well, which is exactly the quantity a mechanism that blows gas out of the galaxy would respond to. The black hole and its host, in other words, have grown up together, and something must couple the one to the other across a vast gulf of scale. That coupling is feedback, and it works in two modes. In the quasar mode at high accretion rates typical of gas-rich young galaxies, the engine's radiation and winds drive fast, galaxy-wide outflows that heat and expel the cold gas, and this is self-limiting, for once a black hole grows massive enough to blow its galaxy's gas away, it starves itself, plausibly setting the very relation we observe. In the radio mode at low accretion rates typical of massive old galaxies, the jets inflate great bubbles in the hot gas that fills the galaxy and its cluster, bubbles seen directly in X-ray images, reheating that gas and preventing it from cooling to form new stars. Feedback of this kind resolves a long-standing failure of galaxy formation models, which without it produce far too many overgrown galaxies. The black holes act as thermostats, shutting down star formation in the largest systems and keeping them old and red. Finally, the population of active nuclei evolves across cosmic time. Quasars were far more common in the young universe, their activity cresting around 10 to 11 billion years ago, the same epoch at which star formation peaked, binding the two histories together, and they show a curious pattern called downsizing. The very biggest black holes finished growing earliest, while smaller ones kept building later, the opposite of how dark matter structures assemble. A beautiful accounting argument ties it all together. The total mass locked away in black holes today should equal the sum of all the light ever radiated by quasars over cosmic history, divided by the efficiency with which accretion turns mass into light, and the books balance neatly for an efficiency near 10%, telling us that most black hole mass was indeed built by luminous, efficient feeding rather than grown in the dark. Yet real puzzles endure, and honesty demands we name them. We do not know how the very first black hole seeds formed, whether from the collapse of the earliest massive stars, or the direct collapse of great clouds of pristine gas into 100,000 solar mass seeds at a stroke. We do not fully understand how quasars harboring black holes of 1 billion suns already blazed less than 1 billion years after the Big Bang, straining every limit on how fast a black hole can grow. A puzzle the Webb telescope has only deepened, turning up a strange population of faint red points that may be overweight black holes in the infant universe, and we cannot yet say what sets a black hole spinning, or a jet roaring, or what truly divides the radio loud from the radio quiet. Active galactic nuclei sit at the crossroads of fundamental physics and cosmology, testing gravity in its strongest regime, lighting the early universe as its brightest beacons, and shaping the galaxies in which we live. The engine is understood in outline, its origins and its grip on the galaxies around it remain the frontier.